Hi class, what I want to do in the next couple minutes is to go over what conformational isomers, or more popularly called as conformers, are. So what you're looking at is butane. We have one, two, three, four. If it's a conformational isomer, what that means, like I said in class, you would be able to rotate the single bond, and perhaps you would be able to go from the way it's drawn to now both the methyl groups facing on the same side. So if you envision the two different ways of writing these structures, we talked about the Newman projection, and I referred to a sideways sawhorse projection as well. For the purpose of the test or the course, we are going to lay a little bit more emphasis on the Newman projection, but just recognize the difference between the two. A Newman projection is something that is seen sort of from the top view, whereas the sawhorse is the sideways sawhorse is the side view of any molecule. So you can perhaps envision, if I draw my butane, maybe here is the horse, here are its ears, the two hydrogens, right? And you have a hydrogen here and a hydrogen here and the methyl. So one can envision that the hydrogen and the methyl are making up the feet, and this hydrogen over here is perhaps its tail. Get the horse? Hopefully you do. All right. But like I said, we are going to lay more emphasis on the Newman rejection. So let's take a quick look at how we draw that and where do we begin. Okay, so I said in class that you have to view through a bond. So where irrespective of whether you want to view along the C2, C3 from the back side, or whether you want to view it from the front side, recognize that both C2 and C3 are going to contain two hydrogens and one methyl group. So this is where I'm viewing it from. Okay, that's my eye, that's my lashes, that's my eyebrow. So that's what you're looking at. Okay, so top view should contain a methyl group on top, should contain a hydrogen on the side, and a hydrogen on the other side. Recall that the front carbon is the small little atom, and the back one is the larger atom. And so if you have the two hydrogens like that, and the methyl is going to be on top. I should draw that, hold on. Need to erase that and draw it on the other side, because it should show the same side. Why is it not taking? Okay. Such a structure where atoms are on top of atoms, we talked about that, that would be called as an eclipsed structure. And if you try to give it a rotation, and every time you give it a rotation, that theta, that dihedral angle, the dihedral angle is the angle between these two like groups, that's going to be 60 degrees. So recognize that if I give it a rotation, you should give it a rotation only one carbon at a time. So you have your front carbon, and now you're going to see a CH3, an H, and an H. Notice that these two CH3s are somewhat like approaching each other, but they are not on top of each other. So this is a staggered unit, and specifically we call this a staggered gauche. When you give it another rotation, so now theta will be 120 degrees, you're going to see a CH3 on top, H and H. On the back carbon, you're going to see a CH3, an H, and an H. So we have gone back to our eclipsed structure. And if you recognize, we will have an eclipsed CH3H interaction. We will also have a CH3H interaction. But if you compare in terms of energy, the interaction with respect to the two methyls that we had for the first eclipse, recognize that this is going to be much smaller because the methyl group is big, but the hydrogen is way too small. And now if you give it one more rotation, hopefully you can see that we are going to get essentially a staggered, and look at that, what that would look like. So we will have our front CH3, H, front carbon, H away, and the methyl group is away as well. So recognize that this is a staggered unit, and more specifically this is a staggered anti, and I'm calling it a staggered anti really because when I compare my theta, which is the dihedral angle, versus the energy, and you start with an eclipsing, and the eclipsing of the methyls, I said that that is highest in energy, followed by the staggered gauche, so that would be lower in energy. Always the staggered is lower in energy as compared to the eclipsed, because that torsional strain that we discussed in class, that would be missing in that case. You can take it one step further, and we talked about that eclipsing and those two methyl hydrogen eclipsing that was going to be higher in energy than the staggered gauche, but lower in energy than your eclipsed with the methyl and the methyl. Recognize when you're drawing these, you have to make sure that that I am able to see in your diagram, which means you're going to see that in the test of some molecule, as well as, of course, that's a part of your mini case as well. So recognize that there should be a difference between the energy difference here and the energy difference here, because those are two different conformations. The 180 degrees, which is the staggered anti, is going to be least in energy. So let me just draw those real quick in case you've forgotten from the previous slide as to what they look like. I had the methyl on top of methyl, hydrogen on top of hydrogen, this hydrogen on top of hydrogen. We gave it a 60-degree rotation, CH3 on top, and we had the methyl over here. Also recognize that you can't, once you draw the bond, you can't just leave it like a straight line, because that would mean that there is a methyl group. You have to make sure that you draw out that hydrogen. And then we gave it one further rotation. So just for clarity, it's a good idea to always draw out your structures at that location. So this is the two CH3H interactions that I have been talking about. And of course, my anti will have the two CH3s is the anti. The 240 is one more rotation. So hopefully you can see that will be eclipsing. So that would be same as the previous eclipsing, because recognize there will be one methyl hydrogen over here, there'll be one methyl hydrogen over here, and these two hydrogens will be the same, of course. So it will look very similar to if I were to number A, B, C, D, and E. I can say that C and E are going to go hand in hand. So I have my CH3, I have my H's, I have my CH3, I have my H here, and my H here. And now if I give it one more rotation, it's going to become staggered. So recognize eclipsed and staggered also basically alternate. And so you're going to see something very similar like B. So you have your CH3 in a gauche, it's approaching that methyl. And as you give it a final rotation, it's going to go back to the same energy as A. And that's the complete eclipsing that we have discussed. So methyl on top of methyl, H on top of H, and H on top of H. Okay, so if you were to really graph it out, you will go from A to B to C to D to E, F, and G. Now, somebody might say, well, is that going to be the same? So in that sense, is there going to be like this mirror image that the two graphs are going to be exactly the same and you kind of hit your midpoint around the anti? The answer to that is no. It really depends on your molecule. I'm about to solve another one, or you can actually use like a different way of viewing for the same molecule, and you'll see that the energy profile is going to be completely different. Let me just talk about that in the next video.